Hello and welcome back. I actually managed to find the mistake and fix it. It was not a big bug. It was just... And I kind of wish that I would have shown you how I fixed it, because then you would know how to debug these kind of structures. I don't know. I guess you can figure it out yourself. I hope so. Yes. And the problem basically was that not only the RAM address, which we defined previously as 16, is actually 31, as we can see here. Totally makes sense. At least not the RAM address, but the actual RAM itself is location 31 in our build, right? Then what is the next thing? Oh, we previously also had the problem that this line of code would jump back to the beginning. I don't know if this is on tape. If it was just a bug that I fixed on my own. The problem was that out as well as in and out, were defined wrongly. They were defined as 6, but they're actually 7. Right? Six is the counter, as we can see. So now, it will work the way it is supposed to be. Maybe we can speed it up a little bit, since it already completed 8 tests. We're pretty sure that it is. Low gate cost, but slow memory. It's interesting because it seems like we just unlocked the RAM. We previously already had the RAM, right? Interesting. Where's test 1? Ticks. Oh, and we already, we also unlocked the gate score by now, right? And the gate score for this level is 8048. And since we unlocked the gate score, it was in the conditionals level, right? When we finished our second architecture, the lag architecture. This one is a gate score of 8000 and 8048. There it is. And yes, maybe we can also remove this window by now. These gate scores will add up, and we will be able to, like, we will create a 8 gate score, right? That is basically the sum of all the gate scores combined. We can see here that, and this this corresponds to the number of NAND gates that we used in the levels, right? 48 gates, 28 gates, 278 gates, 202, 28. Yeah, this is the number of NAND gates. And as we can see, it escalates pretty quickly. This is probably, this is the NOT gate, which is, yeah, just one NAND gate. Here we create the other gates. I think we've created them in a way that uses the least possible NAND gates. At least I don't know. I couldn't think of a lot of better ways. I guess there might be ways, but this is how we did it, and we can then profile. I think this will open a link in a browser. I don't want to do that right now. Maybe it doesn't. I'm gonna click it. Let's find out. It actually does open a link in a browser. Look. This is our total NAND gate score for now. 16,467. On ticks as well, right? Ticks. The less ticks we use, and this becomes especially relevant in the programming levels. The less ticks we use, the better the tick score. The tick score, which is basically, I don't know, the less lines of code you write. No, this is not true. It matters the amount of ticks that it takes to solve the game. And now we're at 78% completion. So we are going to play another level now. Delay, shift. This is going to unlock new components. I guess we want to do that now. Stack is up basically. I don't know if the stack is going to unlock new components. So let us do shift. Shift the value one left. Just means moving all the bits in a byte to the left by one position. For example, 90 shift left 1 would become this. 90 shift left 3 would become this. Oh, this task in this level is to shift the first input to the left by the value given and the second input. The second input will never exceed 7. Inputs, output. So now we would have to create a component that enables us to shift. We could chain these 1, 2, 3 and do this 7 times. It makes sense that it never exceeds 7, right? Because in case we would exceed 7, it would always be an empty byte that we create. And then we would just build this in a way that, let's build it. Oh no, we cannot copy. Just copy. Oh yes, we can. This is fine. So this is shift 1. Right? Or is it? Wait. This is shift 1. Shift left. One, 2, 3. 4, 5, 6, 7. And then we would decide, depending on this input, which we can just decode, since it will never exceed 7. And then if we wanted this component to be more powerful, or build it in a way that would be that would enable us to shift more than byte size, we would then, let's use switches to decide. We would just have to build a bigger structure. But I guess that we will not have to build this by hand, it will just unlock automatically. Nice. That's just what it is. 1, 2, 3, 4, 5, 6, 7. And then we would connect this to every single one of these. And in the end we will output it. Here we go. Alright, we made a mistake. What is the mistake? 0. Oh, we didn't account for the fact that there also is the scenario in which we don't want to shift, because we get the input of 0. Of course. So this will solve it. In addition to giving you a shift left component, we also had the intern create a shift right component. All you had to do was to create the mirror version of this schematic. Nice. I recommend that you add shift left and shift right to your hardware for future levels. Ah, look, there's the 64-bit shift left, which enables us to basically, I don't know, shift 64-bit words, whatever they are called. Product of nibbles. This is not what we're going to play right now. What we're going to play right now is the stack level, because I know that it is finishable quick. In order to cut spending, it has been decided to change the queuing system at public offices so that fewer people will go. Instead of first come, first serve, we are implementing a last come, first serve policy. Think of it like a stack of numbered slips where the citizens either put a slip on top called push, or the bureaucrats take one of the top of the stack called pop. We want you to implement this new system. Yes. Tick inputs. Each tick. The inputs will either signal push or pop. If it is push, store the value on top of the stack. When it is pop, remove that value from the stack and output it. The output has an enable pin. Enable it only on pop. This is good. So what we will do is it's going to be the value. This is what we are going to output. Or can we push and pop at the same time? First of all, when we push, when we pop, we activate the output. When we push, oh, and we load. When we push, we save. This is the next thing that will happen. So here we are. And we're going to use a register. And we're probably going to use an adder to subtract or add one. So in case we push, right, we would then add 1. And this is going to define the address. In case we pop, we then want to subtract 1. Gate. So does this work? No, it does not. So 4, it works. No, it does not. And the reason for that is that we don't save. should always save. And it should always load. It should be always on. Okay, the problem is that we actually have the correct value. We're going to use a mux to handle this inside of our register. But the problem is that it outputs the previous value. Your circuit has been saved to the component factory. Nice, we solved it. Component factory. Oh, great. So the stack is now a component in our component factory. Does this already exist? Oh, we don't have custom components in this level. Okay, it's going 601. Push and pop. In the lab. Let us have a look. I guess the lab is welcome to the lab. Like the component factory, this is not a normal level but a tool. Programming on buggy hardware is very frustrating. It is painful to suddenly be forced to reason about circuits when you're in the middle of solving a programming problem. It is tempting to apply a quick fix so you can get back to solving the original problem, but now this quick fix broke something else. In a program that used to work and so on. Therefore, when developing hardware, try to aim for 100% reliability before you start programming. Nice. This level uses programs to test your circuits. When the programs are running, this level checks if the linked components behave the way that you expect. The lab has two extra keywords. Expect. Keyword is used to describe what a value a memory address should hold. Next tick. The first number after expect is index of the linked component. The second number is the expected value. The linked component index is just the order the components are connected up into the program component. The first number after expect is the index of the linked component. Alright, the second number is the expected value. So we would write expect and then we would write two values where the first is the index of the component. The second one is then the value that it should hold. Alright, yeah, expect for example 2 4. Copy 2 R2. Yeah, that makes sense. The value 4 is put into register 2. Here the first line says that we expect the second linked component to hold a value of 4 after the next tick. All linked components are checked against expectations at every tick. All linked components are expected to be 0 at the start of the program, and expectations for memory components only change as you specify. Specifically change the expectations. The one expectations are counters. These are naturally exposed to increment each tick. The second special keyword for the lab is set input. With this you can control the input of the computer. Set input 1 2 3. You can at time also re-import example tests by clicking below Overture. Set input. With this you can set an input. Alright, okay. all the 16, 32, and 42 bits components that you have in the sandbox are now nice. Yeah, this is like the lab, but for whole architectures. Like it is like the component factory. Great. This is cool. And yeah, we're going to finish this video right here before we go into the next levels. Interesting, we are able to do a lot of programming challenges already. Yes, these are the last two levels. This level is going to be especially interesting because at this point we will be able to have a look at the jump command that we are going to implement, which is basically a go to the forbidden statement that makes up basically every loop or condition in modern programming, or like higher level programming languages. We will see why that is, I hope, if you didn't already know. Yes, and then once we finish this and these two levels as well as, I guess, maybe this one as well, we are going to start programming these 1, 2, 3, 4, 5, 6, 7, 8 levels. Yeah, once more, this was Ivy42. Goodbye.